In this video, we're computing a trapezoid approximation to the integral from -10 to 10 of e to the negative x squared dx. So this is our basic Gaussian curve, and that function e to the negative x squared has no analytic antiderivative, which is why we're looking at a numerical approximation of this integral. Now, the starting point in setting up a numerical integral is to determine the subinterval width. So if we want to chop this area into 50 trapezoids, we have to have a bunch of cut points along the x-axis, and this defines 50 subintervals. Each one of those is going to have a trapezoid defined on it. So we're going to call our subinterval width, we'll call that delta x. And that's just the total interval width, which is 20, because we're integrating from -10 to 10, so that's 20. Divided by how many subintervals we're chopping it into, which was 50. And this gives us a subinterval width of 0.4. Now the next thing we want to do is come up with a general expression for the ith cut point on this interval. And on the left side of the subinterval, we would normally call that x0, that's our starting point, and x0 is equal to -10 in this case. And then all the way on the right side of our interval, we have x50, that's our 50th cut point, 50 steps to the right of the starting point, and that occurs at x equals +10. So to write down the ith position in all of these steps, and we call that x sub I, we always start at our starting point, x0, and then we step I steps to the right. So this is always just our starting point at the left end of our interval, plus I steps to the right, and the step size is delta x, which we already computed. So now all we have to do is plug in what's our starting point, and that was -10. And then I want to bounce I steps to the right. Our step size is 0.4, so we end up with a term that says 0.4i. So now we're ready to talk about the area of our trapezoids. So let's zoom in and get a better look at some of those trapezoids toward the center of the picture. Okay, so now we're zoomed in on the 10 trapezoids that are closest to the center of this curve. And one interesting thing to note here is that toward the center, I can see that my trapezoids are underestimating the area under the curve. And this is actually because the curve has downward concavity in that region. Then the curve is going to inflect to upward concavity. And if you look really close at the trapezoids out here, you can see they're slightly overestimating the area bounded by this curve. So with any luck, those underestimates and overestimates will help to offset each other and give us a really accurate approximation. Now the way we find the area of a trapezoid, if I just mark a couple arbitrary cut points here, I'm just going to call this xi minus 1 and xi, just two consecutive cut points. The way we get the area of a trapezoid there is by measuring the height at the left side and the height at the right side, and then averaging them. So I'll just go ahead and call this individual area. I'll call that AI. So what we're going to do is take our function, which is e to the negative x squared, and I'm just going to call it f for the moment. And we evaluate that at the left side. That gives us the height at the left side of the trapezoid. We evaluate that at the right side of the subinterval, giving us the height at the right side of the trapezoid. And then we just take the arithmetic mean of those two values. So we add them together and divide by 2. And now we multiply the average height by the width, which we already have a name for. That's delta x. So there's the area of an individual trapezoid. Okay, so next I'd like a general expression for the total area under the curve on the interval -10 to 10. And I'll just call that capital A. And we'll say A is approximately the sum of the areas of all the trapezoids. So each one has an area that looks like this. It's 1/2 times the sum of the left and right heights. That's the average height, multiplied by the subinterval width. And now we need to figure out how to index this sum so we're adding up all the trapezoids correctly. So I want to point out that if we started the sum at I equals 0, that's problematic because it would make it so this first term here, that would be f of x -1. That would be one step to the left of our starting point, which remember was x0. So our starting point must be I equals 1. And just to make sure it's working correctly, if I evaluate that in this first term, I get f of x0, which is the height at the left end of our first subinterval. And right here, I would get f of x1, the height at the right end of our first subinterval. So we know our starting point is working correctly. Then we think about the upper limit for our sum, and we know we need to have 50 trapezoids here, so I better have 50 terms in my sum. So I'm going to terminate my sum at I equals 50. And you can always double check this as well. If I look at the first term in my sum here, x sub I minus 1, this height is going to be f of x 49. So that's one cut point before the end of our interval. And our final height is going to be f of x 50, the height of the right-hand side of the last trapezoid. So everything is working beautifully here. Now all we have to do is sub in our function f of x, and that's e to the negative x squared, and evaluate that at xi and xi minus 1. And those are given by this expression we wrote down for xi. So to get xi minus 1, you just replace I with I minus 1. So we have the sum from 1 to 50 of 1/2 times our function evaluated at xi minus 1. So this is e to the negative xi minus 1 squared. So xi minus 1 is negative 10 plus 0.4 times the quantity I minus 1. And we have to square that whole thing. And then f of xi, that's going to be e to the negative xi squared. So negative 10 plus 0.4 I all squared. And then don't forget to multiply this by the width of each trapezoid, the subinterval width, 0.4. Okay, our sum is fully set up in terms of I, and we're ready to use technology to get a decimal approximation on this thing. And today I'm using an arcane computer algebra system called wxMaxima. And the coolest thing about Maxima is that it's open source and it's a free download. Okay, so the syntax for this is going to be pretty similar for any computer algebra system. What we've done here is input the summation notation. So our sigma notation just turns into sum, and then we put in our 0.5, and then we have our first exponential term in here. That's the one evaluated at I minus 1. We add in the second exponential term. That's the one evaluated at I. There's our subinterval width, 0.4, and then we add all these up as I goes from 1 to 50. Finally, this whole thing is wrapped in the float command, which forces a floating point decimal approximation. And we hit Shift Enter to execute. And we get an approximate value of 1.772 and so on for this area. Okay, so there's the approximate value of our trapezoid sum. But I want to check this against the built-in numerical integration algorithms in our computer algebra system. And in Maxima, that's the quad QAG command. So now we just entered this thing like we're doing the integral. We just put in the function e to the negative x squared, and we integrate from negative 10 to 10. And the last number there is really just selecting which algorithm is going to be used to approximate the integral, and it doesn't really make a difference which one we use. Shift Enter to execute. And we can see we're actually getting remarkable agreement between our trapezoid approximation and the built-in numerical integration algorithm. So when I check out these two approximations, the first disagreement between them is in the 15th decimal place. Now an n equals 50 trapezoid approximation is normally pretty good, but not that good. And the reason this one ended up so good is that this underestimate of the trapezoids that are right toward the center is just beautifully offset by the sum of all these slight overestimates that occur after the curve inflects to upward curvature. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.